Here we go. We're going to learn how do we detect earthquakes in this lesson. It's a short lesson on seismographs, how they work, what they do, why we need them. And to start off with, we're going to go back a second. If you remember this map, now this map has P waves and S waves together, and the S waves are blue, and they are stopped by the liquid inner core. The P waves can go through that core, but they are refracted a little bit, or that they're bent, and they end up down here, and there's these shadow zones. Well, what this means, wherever there's an earthquake on Earth, and it doesn't have to be just up here, wherever this earthquake is on Earth, let's say it's in Alaska, on the opposite side of the Earth, they're picking up only P waves. But the thing is, those P waves are very, very weak. If the earthquake happens in, let's say, Japan, all right, well, down in South America, they're only picking up very, very weak P waves. Here in the United States, we might be getting both, but they're also very weak because it's so far away. And how do we measure these things? How do we know an earthquake happened that far away when it's such small waves at that point? The answer is with seismographs. Now, if you take a look at these, you'll see that there's always some sort of mass here, and attached to the mass, there's a pen. Okay, so what happens is the Earth can move. In this case, this is a vertical seismograph. The Earth moves, the paper moves, the pillar moves, everything here moves except for this mass and this pen. This mass and this pen stay in pretty much the same spot while the paper moves up and down near it. In this case, the mass stays in the same place while the Earth moves side to side. And because the mass stays in the same spot, the pen stays in the same spot, it draws a little line on the paper that you can use to measure and compare. So if one earthquake happens and it draws a little line, and then the second earthquake happens and it draws a little bit bigger line, you know the second earthquake was immeasurably bigger than the first one. So here's what these are. Seismographs measure the shaking of an earthquake. Okay. A mass stays stationary while the Earth shakes, the paper underneath of it. Here's a video of how this works. Okay, so here is our mass right here. Now, as we move the paper underneath it, that little pen will make a line on the paper. Okay. Now, the mass stays still even if there's an earthquake happening and everything's going side to side, back and forth. This is what we use to measure earthquakes. So we know how big they are, we know how powerful they are. We can start figuring out how far away they are. We'll see in the next lesson. Now, we don't use paper ones everywhere anymore. These are the fancier ones. This is electronic. So what we have here is a magnet next to some metal, and as this magnet gets shaken back, or excuse me, as the magnet stays still and the Earth shakes back and forth underneath it, that makes a little bit of electricity come in here, and basically a computer can digitally record what's going on in the Earth. Okay. Similarly, you might see some of these on big drums as well. That's how we do it today. But the idea is the exact same. Something stays still while the Earth shakes underneath it. Okay, so those are seismographs. Now, reading a seismograph, what we end up with is something that looks like this. Okay. Now, when there's a still line, there's no earthquake happening. Now, when the earthquake starts, the P waves arrive first, and they're these little squiggles. The S waves show up right here. And the other detail I want you to know is that this here is the amplitude of that wave. So we can measure this. We can measure from here, we can measure to here, and this is the amplitude. Now this is important because if the next earthquake shows up, maybe this was a foreshock, now the next earthquake's showing up, here are the P waves, and the S waves start, you can measure how much more powerful the second earthquake is compared to the first earthquake. So the amplitude of the wave is an important word we need to know here. For the notes, the P wave always arrives first, the S waves always arrive second, and they are more destructive. Last thing on your page here has to do with wave. Okay, so this chart is a little different than most speed charts. We have distance down here at the bottom, and we have time on the side. That's flipped from what you normally have. So if you take a look at this, it's the opposite of what you expect. The shear wave is the slower one, and the compression wave is faster. Think of it this way. After 10 minutes of traveling, the S wave has only gone 3,000 kilometers, while the P wave has gone 7,000 kilometers. So if you read it that way, it makes a little more sense. Now, P waves are the fastest, you'll see on this chart. The S waves are definitely slower. Now, what we're going to be doing here in the future is this. You can find how far away an earthquake was by measuring the distance and arrival time. So here's what that looks like. Let's just say that the P wave shows up, and then 10 minutes later, the S wave shows up. So there's a 10-minute gap between the P wave and the S waves. Well, if we go down here, we're going to see, well, if we were 4,000 kilometers away, there would be, this is 6 going up to 13. That's a 7-minute gap. So if we were 4,000 meters away, there would be about a 7-minute gap between them. So we must be further away than that. We're going to practice this more later, but the answer in this case, 10-minute gap is right here. So at 10 minutes, the compression wave has moved about 7,000 some kilometers. The S wave will take 10 more minutes to get there. So we'll practice this in the future, but basically you can find out how far an earthquake is by measuring the difference in arrival times. More on this later. So make sure you ask any questions, but pretty short lesson.